Today in the workshop, we're working with USB power delivery. You'll see how USB-PD can supply your projects with higher voltages and currents than standard USB. We'll also look at advanced modules that let you manage all that power with a microcontroller. It's a powerful episode today, so welcome to the workshop. Well, hello and welcome to the workshop, and today we are going to be working with USB-PD, or power delivery. USB-PD is a technology that allows you to go far beyond regular USB when powering your projects. Unlike regular USB, which is limited to 5 volts at relatively low currents, USB-PD can supply high currents at voltages up to 20 volts. A USB-PD power adapter is an intelligent device, and your project needs to negotiate to get the level of power that it requires. Once it does, it's given a constant level of smooth DC power that you can use to power everything from microcontrollers to stepper motors, LED strip lights, you name it. So today what I'm going to do is show you how you can use USB-PD in your project. It's very simple and inexpensive to use. There's some very inexpensive adapters that we'll be looking at, and we'll also be looking at some intelligent adapters from both Adafruit and SparkFun, ones that you can connect to microcontrollers and control and measure voltages yourself. So before we do that though, the USB standard has been with us for about 30 years and it's gotten a bit confusing. There's a number of different connectors. There are even different color USB jacks. What's that all about? So what I thought we would do before we started working with USB-PD is learn a little bit more about the universal serial bus. In the mid-1990s, a group of 7 information technology companies got together to create a new connectivity standard. In 1995, Intel, one of the members, created the first integrated circuits for what would become known as the Universal Serial Bus, or USB. The Universal Serial Bus was created in order to eliminate the serial and parallel cables used to connect computers to peripherals such as modems, printers, and mice. It's also been used to provide power for these peripherals. In the nearly 3 decades since its inception, USB has used a number of different connectors, such as the common Type A and Type B connectors, today's modern Type C, the mini and micro connectors, as well as super speed connectors. These connectors vary in shape as well as the number of wires that they use. The USB Type A connector is the most common USB connector and is often used for host controllers such as computers. It can also be used on hubs and charging devices. This is what's known as a downstream data connector. USB Type B is used for peripheral devices like computers and Arduino Unos, and it's an upstream connector. The original USB A and B connectors had 4 wires: V-bus, which is the positive 5 volts DC, D- and D+, which are the data line, it's a balanced line, which is why you have a minus and plus, and a ground connection. USB would eventually evolve to have micro and mini connectors. The micro A connector is interesting in that it can be both a host controller or a peripheral device. It can be a downstream or upstream connector. The mini connector can just be a peripheral device or upstream connector. The reason the microconnector can be used for both a host and a peripheral device is the addition of the ID line. The ID line supports what's called USB OTG, or on the go, and can be left grounded or open to indicate whether the device is a downstream or upstream device. You can buy cables that have this line grounded for devices that don't support USB OTG. The modern USB connector is a USB Type-C connector. This can be used for host controllers, peripheral devices, and for hubs. It can be both a downstream connector or an upstream connector. USB Type-C uses 12 wires, but the connector itself actually has 24 pins. The other side is a mirror image of the first side, so the connector can be reversed and used either way. Over the years, the USB standard has improved in both terms of data speed and power capability, and with USB 3.1, a new capability was introduced to provide voltages other than 5 volts and currents up to 240 watts with the latest version of USB. This is called USB-PD. USB-PD is USB Power Delivery. It was defined by the USB-IF, or Implementers Forum, in 2012. USB-PD was released with USB version 3.1, and on the device end it requires a USB-C connector. USB-PD can define a number of additional voltages, although the power supply will default to 5 volts. It provides increased current capability and also the ability to do bidirectional charging. Bidirectional charging works as follows. Let's say we have a phone that is connected to a USB-PD charger. The phone will negotiate with the charger to get the power requirements. Once negotiated, the charger will adjust its voltage and send the power to the phone. After the phone is charged, it can be used as a power supply. A second phone can negotiate for power requirements, and the first phone will adjust the voltage and send the power to the second phone. USB-PD requires a USB-C connector, and it uses a couple of specific pins on the connector. The control communication line is used to negotiate the power requirements for the USB-PD device, and V-bus are the standard power connectors for USB. There are several varieties of USB-PD chargers available. Not all USB-PD chargers can supply all 5 voltages, though. You'll have to check the label to verify the voltage and current capabilities of your charger. If the charger can't supply a voltage, it'll be defaulted to the next available lower voltage. So for example, if the charger does not have 15 volts available but has 12, it will supply 12. Don't confuse USB-PD with Quick Charge. Quick Charge, or QC, is a proprietary standard developed by Qualcomm, and it does basically the same thing as USB-PD, but it works in a different fashion and is not compatible. Many USB-PD chargers use gallium nitride or GaN semiconductors. These are much more efficient than silicon transistors, and they can provide for a higher power in a smaller package. Another important consideration for USB-PD is the cables that you're using. Some USB-C cables are for power only. They can't be used for high-speed data and often have thicker conductors for the power lines. Longer USB-C cables can reduce the power delivered to your device, especially for high current devices. You should try to use as short a cable as possible. Only select cables that have been certified by the USB-IF for use with USB-PD. That way you'll be sure your cable is good. You'll also want to check the power rating on your cable, and this is usually specified in watts. Over the years, the USB Type-A connector has been redefined, and a color code has been established for these connectors. Note that this is not an official color code, but most manufacturers follow it. The blue, teal, and red USB-A connectors have 9 connections instead of the standard 4. Physically, the connectors are arranged so they're backwards compatible with the older connectors. USB-PD has opened up a whole new world of devices that can be powered by USB. USB is not only now used for things like tablets and phones, but can be used for computers and even tools such as soldering irons and electric drills. Of course, we can also use USB-PD for our experiments, whether we're trying to get 5 volts for a microcontroller or different voltages to power motors, charge batteries, or drive LED strips. So now let's start working with USB power delivery. Now I've got a few USB-PD power supplies for you to take a look at over here, and as you can see, they're all very different looking, and of course they all have very different specifications. Now one thing you should be aware of when you're choosing a USB-PD power supply is that not all of them support all the USB-PD voltages. For example, this one here only supports the 5 volts, 9 volts, and 15 volts, so it doesn't support 20. And this one only supports 5 volts and 9 volts. Now Now, these other ones support the full range of USB PD voltages, including 12 volts, which on some supplies is kind of rare, and they have different current capabilities. You will find a label on all of these supplies that indicate what their voltage and current capabilities are, so you'll need to check that out when you're choosing a USB PD supply. Now, some of these supplies also support quick charge. For example, this one here, the USB Type-C adapter on it is for USB PD, whereas the Type A adapter is for quick charge. So remember, quick charge works like USB PD, but it is not the same and it is not compatible. Now, my personal favorite is this one. It's the one I use on my workbench. I like it a lot because it has a lot of output power. It's got a total of 240 watts between all of its ports. It supports both PD and quick charge, and I like the digital display. It tells me both the voltage and the current I'm consuming. So I've got this little tester for my workbench that uses USB-C to charge it. I'll just plug that into it. And as you can see, it's telling me on port number 1 where I'm on, I've got 5.19 volts and 1.1 amperes of current. And it's really handy to know that. Now, I'll take another USB-C device. This is a USB-C soldering iron. And I'll plug it in and turn it on. And as you can see, the voltage goes up to 20 volts right now, and it's pulling about 2 amperes. Now it's dropping as the iron is heating up, and I'll unplug it at the moment. Now, if you have a USB PD supply and you don't have a display, it's a handy thing to have, and you can buy these little adapters. This is a relatively cheap one. There are fancier ones than that, but they just plug in line, and they measure both voltage and current, so it's a really handy thing to have. So let's just plug this in and turn my supply on again. And as you can see, I also get a display over here now. And so that's really good to know, especially when you're experimenting with USB PD power supplies, which is what we're going to be doing today. So now that we know everything there is to know about USB PD, it's time to start working with it. But before we do, I want to mention that if all we want to do is get 5 volts at a relatively low current from a USB-C connector, there is another way of doing it, the way that gets you the conventional USB power. Now, with older style USB, you used to just tap onto the V-bus line. The V-bus and ground would give you 5 volts. And it will do that on USB-C as well, but there's an additional consideration. The CC line, the control communications line on the USB-C cable, is used for a different function in this application. If you hold the line high, then you're indicating that you are a USB power source, a source of power. If you hold it low, it indicates that you're sinking power, that you're a device that consumes power. And that's what you want to do. You want to tell it that you're a device that consumes power. So what you need to do is connect 2 5.1K resistors between the CC1 and CC2 lines to the ground on the side of your device, and that'll tell your power supply that you are a sink, and it will give you the 5 volts of power. The reason for the 2 resistors, of course, is that the USB-C cable is reversible, so when you reverse it, you want the 5.1K resistor to be there. But assuming you want to get more than 5 volts and all those wonderful different currents I told you about, then you want to use USB PD, and the way to do that is with something called a PD trigger board. A trigger board triggers the USB PD power supply to give you the voltage and current that you want. They're very inexpensive and they're very easy to use. So let's go and take a look at a few USB PD trigger boards. Power trigger modules are devices that can select a specific voltage from a USB PD charger. These modules perform the negotiation with the USB PD power supply. You can use these modules to convert legacy non-USB PD devices to USB PD. You can also use these modules to test USB PD chargers and supplies. And of course, we can use them to power our electronics projects. There are many power trigger modules available. Here are a couple of popular ones. The HUSB238 is a module that supports role swapping, so it can allow your device to be both a charger and a device that consumes current. The ZYPDS trigger module is one that uses resistors to select the output voltage. The PDC004 is an interesting trigger module in that you purchase it with a fixed voltage, so you select the USB PD voltage you wish and pick up a module with that voltage. And a very popular module is the ZY12PDN. This is a 100-watt module that uses a push button to select the voltage. The ZY12PDN is very easy to use. It's got a USB-C input for the voltage and a terminal for the DC out. There's also a push button to select voltage and an indicator to show you what the voltage actually is. It can be run in two different modes. In selectable mode, it defaults to 5-volt output. You can use the push button to select the voltage, and the indicator will display the output voltage as shown in this chart. Note that in selectable mode, it'll reset the 5 volts once you unplug it and plug it in, so you need to be aware of that. The other mode that you can run the ZY12PDN in is the programmer fixed mode, and here's how you accomplish that. First, you remove the USB-C cable from the device. You hold down the button and then insert the USB-C cable. Then release the button. The voltage indicator will rapidly flash, and you can now use the button to select the voltage. Note that there are two additional selections in this mode. The purple indicates the highest voltage. In other words, it'll pull the highest voltage that the USB-PD power supply is capable of. White mode is an interesting one in which it will cycle through all of its voltages, and while that may not have too many practical applications, it can be used to test USB-PD power supplies. Let's pull out a ZY12PDN module and give it a try. Now, before we start working with the ZY12PDN, I want to show you a few power trigger modules. I've got a couple of other ones over here. Now, this is the ZY12PDN module itself, and that's the one we're going to be using today. And you see it's a pretty compact little module, pretty easy to work with. Another really little module is this one here, and this is a fixed voltage module. You buy these in the USB-PD voltage that you want, and then you select it. For example, this is a 20-volt module, and I'll demonstrate it for you in a moment, but look how tiny this thing is. It's amazing. Now, this is a module I wanted to show you only to say it's not one we're going to be using, the LXQC03. This is a very popular module. You'll find this all over Amazon and eBay. The reason we're not using this is that this is not a USB-PD module. This is a quick charge module, and it's meant to be used with quick charge chargers. But if you're using quick charge and you want an equivalent, this is a good module to use. Now, as I said, with this tiny module, I've got a little demo arranged, and I want to show you how we're going to be testing our modules today. Over here, I've got just a resistive load. It's just two power resistors, two 16-ohm resistors in series, so I got 32 ohms of load. And I've got a voltmeter attached to it as well. And right now, I've got one of those little 20-volt modules on it, so I'm just going to plug that into my USB power supply. And you can see it goes right up to 20 volts. And you can also see that I've got a multimeter on here, and it's measuring the final voltage. You'll also notice some discrepancy between the two voltage measurements, and a lot of that has to do with the voltage that you're losing in the USB cable. They tend to give you more voltage on the supply end to compensate for that. And so this is a test setup we're going to be using. Now we're going to take this module, and we're going to put it to the test. So I've got the ZY12PDN hooked up to my USB-PD power supply and to my test load, and the voltmeter says I'm getting 5 volts out, which is also indicated by the red LED. And if I press the button, the LED changes color, and as you can see, I get a different voltage. And I can cycle through all the different USB-PD voltages I've got here. Here's my 20 volts at the top, and then I'll go back to the 5 volts again. Now, one thing that I noted earlier was that when you first plug this in, it's always going to revert to 5 volts. If you want to set it to a different voltage, you need to go through the procedure I described, where you take out the USB-C cable, hold the push button down, put the cable in, you'll get a flashing light over here, and then you can cycle to a voltage, and once you pick that voltage, it'll be its permanent voltage. But otherwise, it's a pretty easy module to use and a great way for powering things with a USB-PD power supply. The Adafruit HUSB238 is a power trigger board with a bit of a difference. It can be used in the same fashion as the PD trigger boards that I just showed you, but it also has an I2C connection. And with the I2C connection, you can use a microcontroller or microcomputer to set power levels, to read the levels available on a USB-PD adapter, and a few other things as well. It's a very easy board to use, and so let's go and check out the Adafruit HUSB238. The Adafruit HUSB238 is a power trigger module with a 100 watt maximum. This device can be configured either using jumpers or I2C. Note that there is no I2C supply or pull-ups on this device, and be aware of the voltages it handles, so be careful when using I2C with this. By default, the I2C address of the HUSB238 is hexadecimal 8. Here are the pinouts of this device. The SDA, or I2C data, and SCL, or I2C clock, are on the first two pins. The V plus pin is the output of the device, and there are two locations for it, on the edge of the board and another one used with a terminal strip. The same arrangement is used for the ground connection. Finally, there are two connections for the D- and D+, the data line on the USB connector. The terminals on the right side of the board perform the voltage selection, and the terminals on the left side perform the current limiting selection. Note there are two different types of terminals. There are solder bridge terminals, which need to be bridged over with solder to make contact, and cut trace ones, which need to be cut with a hobby knife in order to remove the contact. Let's do an experiment with the HUSB238. We'll bring it an Arduino Uno, and we'll hook it up as follows. We'll connect the ground from the Arduino to the ground pin on the HUSB238. The Uno's pin A4 will be connected to the SDA pin on the power trigger module, and pin A5 will be connected to the SCL connection. V plus is the positive output voltage, and we'll use that along with a connection to ground. Now, the Arduino wire library does have internal pull-up resistors, but they're pretty high value, about 30K. If you find this is operating in a rather intermittent fashion, you might want to add your own pull-ups. Connect two pull-up resistors to the 5-volt line on the Arduino. Make sure not to use the output voltage line on the HUSB238. And this completes our wiring. Now let's go and give it a test. And so I'm testing out my Adafruit HUSB238 board, and I've got it hooked up to the Arduino Uno as according to the diagram I just showed you. I've also got my test load and my meter on it, and of course I'm powering it with my USB-PD power supply. Now I'm running a sketch that Adafruit includes with the library for this board, and you're going to have to install that library first. So go into the library manager in your Arduino IDE and type in Adafruit HUSB238. And you'll get the library. And I've got an example from that library that I'm using right now, this HUSB238 test. And this basically puts the board through its different parameters, but it also tests out your USB-PD power supply for its capabilities. We can take a quick look at how it works. You can examine it in more detail yourself later. Essentially, we start off as you might expect, including the wire library because it's I2C, and the Adafruit library, and then we create an object for the Adafruit device itself. Then in the setup, we do the usual starting the serial monitor and starting the device itself and starting the wire library. And then we'll go into the loop. And here in the loop, we're going to add a little delay. We're going to make certain that the HUSB238 is attached. And if it is attached, we're going to read a number of the parameters from it. And so we're just going to go down and read the parameters. We're going to make queries and get responses. And that exactly is what you do with USB-PD. You make a query to the USB-PD adapter and get a response back. And we're going to find out exactly what voltages and currents we can get out of this adapter by using this sketch. So as I said, I'll let you go through it because it's basically just a lot of function commands and serial prints over here. And so I've got it running right now. And so let's go to the serial monitor and take a look at what it's saying. And there we go. And it's basically a loop, so it just keeps doing the same thing. It shows you the status of attached. It shows you things like the amount of current. It tells you what's available. It notes there's no 18 volts available, and I found that kind of surprising because 18 volts is not a standard USB PD voltage, and that's why it isn't available in my power supply. But otherwise, it shows you the currents and voltages I can get out of the supply I'm connected to. So this is a pretty versatile adapter, and actually as a trigger board, it's not that much more expensive than ones that don't use I2C. And of course, you can use it just as a standard trigger board by using the jumpers, or you can use it programmatically and program it for voltage and current yourself using the Adafruit library. Now, the last PD trigger board we're going to look at today is a bit different than the other ones. This is the SparkFun Power Delivery Board, and it is similar to the Adafruit board in that it is controlled with an I2C connection. It's different, though, in that the I2C connection is the only way to control it. It doesn't have jumpers for individual voltages and current like the Adafruit board does. This board has its own microcontroller, and the microcontroller itself uses a concept of something called a power data object, or PDO. Power data objects are essentially profiles that you set with voltages and currents, and then you call them up when you want that voltage and current. As with the Adafruit board, the SparkFun board is a very high quality board, and also as with Adafruit, SparkFun has provided software for using it with the Arduino IDE. So let's go and take a look at the SparkFun Power Delivery Board. The SparkFun Power Delivery Board is an advanced microcontroller-based USB-C trigger board. It has several features such as voltage transition and high voltage protection. This board will support dual high power charging, so it can act as both a source and a sink. The board is controlled with I2C, and you can either connect using the pins on the side or an onboard quick connector. There's also an optional I2C power input from 3 to 5.5 volts, so you can set the I2C voltage reference. The board's I2C address can be selected using jumpers on the back. The SparkFun Power Delivery Board is based on the ST Microelectronics ST-USB-4500 chip. One of the main concepts of this board are the use of power data objects. These are virtual objects that contain 4 parameters that define a USB PD connection. The parameters are voltage, overvoltage tolerance, undervoltage tolerance, and current limiting. The power delivery board has 3 PDOs. PDO2 and PDO3 are both user programmable. PDO1 has fixed parameters with a 5-volt output. Power data objects work on a priority system where PDO3 has priority, followed by PDO2 and then PDO1. The priority system works so that if the power supply in question cannot supply the required parameters for PDO3, it will then revert to the parameters for PDO2. Now here are the connections on the power delivery board. We can see a USB-C connector for the power input, and a quick connector on the bottom for easy connection to a microcontroller. On the other side, we have ground and V-Sync, and these are both available as pins and a terminal strip solder area. This is the output power from the board. Along the bottom of the board, we have the SCL and SDA connections for the I2C bus. VDD is the I2C voltage. This is an optional reference connection and should be between 3 and 5.5 volts. There's a ground connection and 2 outputs for PDO2 and PDO3. These go low when the PDO is active. The V-in pin contains the voltage directly off of the USB-C cable. There's a ground connection and a D- and D+ for the balance line data on the USB-C. There's an active low alert output for when the microcontroller has an alert, and a reset input that's also active low. The microcontroller also has one GPIO pin, and it's over here. On the side of the board, we have 3 LEDs. The first 2 are the activity for PDO2 and PDO3, and the third one is the activity on the GPIO pin. Finally, the board also has a push button to reset it. On the back of the board, we can select the I2C address. Currently, with the 2 jumpers closed, the address is hexadecimal 28, but you can cut one or both of the jumpers in order to change that address. There are also jumpers available for the I2C pull-up resistors. By default, the board does have pull-up resistors, but you can cut these traces if you don't want to use them. So now let's go and experiment with the SparkFun Power Delivery Board. Now I'm testing the SparkFun power delivery board right now, and I've got it hooked up to an Adafruit QT Pi microcontroller. Now the QT Pi is based on the SAMD51, and it looks a lot like the original Arduino Xiao, and that's not too surprising. It's designed to be compatible with it. It's got the same form factor and pinout, but one thing it has that Xiao doesn't have is a quick connector, and so I used a quick connector to connect everything up to the power delivery board, and it's a very simple installation. Now, as you can see, the power delivery board has a light that's flashing on and off, and so it's running a program right now, a sketch that SparkFun provides as an example sketch. This to change voltage levels, and it's a good sketch because it shows how the PDOs work. And so let's go and take a look at that right now. Now, before you run this sketch, you're going to need to install the library for this, so just go into your library manager, type SparkFun power delivery, and install the SparkFun STUSB4500 library, and it'll give you everything you need. And this is one of the examples called changing voltages that they include with the library. Now, it's a pretty simple example, and what I like about it is it illustrates how to work with the PDOs, and that's really the key to working with this board. So we start off by including the wire library for I2C and the SparkFun library itself, and we define an object called USB. And then in the setup, we do a lot of things. We go and first of all start I2C, and then we go and check the USB. We go and read the USB with USB read, and then we print a number of different parameters from the USB. And you'll note the syntax of a lot of this. For example, this is read the settings for PDO1. So for example, to read the voltage, we do get voltage and we pass it a 1 for PDO1. Now when we go down to PDO2, you can see we do the same thing, but just pass it a 2. So the functions in the library make it very simple. We do a bunch of things to read the configuration over here. We toggle the GPIO pin configuration as well. And then we go into the loop. And in the loop, we start setting the PDOs and turning them on and off. So here we set PDO number 3 to 9 volts. And so we do the set PDO. We pass it number 3. And then we do a set voltage to PDO 3, 9 volts. And we're going to delay it for 3 seconds. Now when we do this, it will not output 9 volts. It only reads the PDOs when it first resets. So what we do next is we do a soft reset. So this is how we do that. And then it will change to 9 volts. And we do the same thing with a number of different voltages. You can walk yourself through the program itself just to see how we do that. And the result is it's going to print a number of things on the serial monitor telling us what it's doing, and we can also watch it on the voltmeter, and we can even watch the status lights on the power delivery board itself. And so let's go and take a look at the serial monitor, which is running right now. Okay, so it's done a soft reset to change the voltage. And so now we can take a look at what it's doing. It's switched to PDO1, which is 5 volts. We can see that on the meter. And also when we go to PDO3 over here, you can see the status light for PDO3 came on. And so you can just run this through. It'll step through its voltages. It'll change the PDOs. And it's really a good lesson on how to work with this amazing board. Now, obviously, this is a pretty sophisticated board. It's much more expensive than the other ones we've looked at. I wouldn't use it for every application, but the PDOs make it possible for you to set different profiles for power and have your device act differently depending on the USB-PD adapter that it's connected to. If the adapter doesn't have all of the features, you can switch to a different voltage and perhaps perform a different function. So it's a very versatile board for those who need that kind of versatility. Alright, that about wraps up our look at USB-PD for today, but it doesn't finish our work with USB-PD here in the DroneBot workshop. I've got another episode coming up where I will show you 2 different USB-PD power supply projects you can build, as well as an episode to show you how you can use this technology to charge batteries up. So this is a great technology, and I'm sure you're going to make a lot of good use out of it. Now, if you want some more information about USB power delivery, you can check out the article that accompanies this video on the dronebotworkshop.com website. There is a link below the video right to that article. And when you're on the website, if you haven't yet, please consider subscribing to my newsletter. No, it is not a sales letter. It's just something I send out every now and then to let you know what's going on in the workshop. And of course, it's free to subscribe. You don't even need to tell me your name. I just need your email address. If you're willing to tell me your name, then you can join the DroneBot Workshop forums, where you can talk with a number of like-minded individuals professionals who can help you out with your electronics projects, or just who like to talk shop. And the forum is free to join. There's information below the video on doing that. And of course, if you haven't yet, please consider subscribing to the YouTube channel. I make videos about electronics and microcontrollers. And if you like this video, I'm sure you'll like my other ones. It's easy to subscribe. All you need to do is hit that red subscribe button. And also, if you click on that little bell notification, and assuming you've enabled notifications, you'll get notified every time I make a new video. So until we meet next time, please take care of yourselves. Please stay safe out there, and I will see you soon here in the DroneBot workshop. Goodbye for now.